Previously, yeah, this one also same. Shear stress. We have another set. Shear stress. Shear condition. You have shear equal to G gamma, right? And this one is, they give you the angle of tangent, L or B, A, theta, all this. Okay. Then we stop at this example. Okay, we stop at example 5. So we continue on example number 6. So before you look at the diagram, so you have a tensile stress. We apply along long axis, so longitudinal axis, on the cylindrical brass rod with a diameter 4 mm. So in the question, normally we won't give you any diagram, so you need to draw. So you have a rod and tensile stress. Tensile means the force acting outside or at the both end, that pulling outside. Determine magnitude of the load required. Need to determine the F here to produce 2.5 10⁻³ mm changes in diameter if the deformation is entirely elastic. So this equation is all elastic equation. All these are elastic. So you need to, when you pull, it will change longer. Will change longer. The L will be longer. And there is a string in your diameter. Okay, so you'll see a diagram like this. So you draw a diagram, the blue one and the red one, and then you pull at both ends. Original, LO, and after the elongation, LI. Okay. And then here you can calculate the strain value in z-axis, which is you take the change of length divided by original length. And the x also. X here, you're focusing on the diameter and not length, because there's a shrinkage of diameter here. Okay, strain, again, strain is a deformation ratio. Okay, it's a deformation ratio. Strain do not have unit, or technically it's just mm divided by mm or mm divided by m, right? So you have two calculations that you can calculate. One is strain in z-axis, another one is in the lateral or in the x-axis. So again, you have two type of deformation or direction. One is if it's in the long way, we call it longitudinal, or if in the side, then we call it lateral. So you have longitudinal and lateral. So that here is longitudinal strain. X here is lateral strain. Okay, longitudinal, lateral. So if the question asks you to find longitudinal strain, it means long way, z-axis or y-axis, right? If it asks you to find lateral deformation, it means the body, the shrinkage of body, all right? So these two is you can calculate again. So keyword here, you have to be familiar with lateral and longitudinal. Two, longitudinal, lateral. Okay, the rest you read, so you can find the strain. Again here, your lateral is shrinking, so you get the negative value. Diameter change from 2.5, the change of diameter is 2.5 10 power negative 3 mm. Original is 10 mm. So you can find the lateral strain equal to minus 2.5 10 power negative 4. Okay, be careful on the index. Be careful on the 10 power something. Remember to change all the mm. To be safe, change to all the use all unit SI if can. So next, you look at the table. If you download the tutorial, there's a table there. So here you're given the brass rod. So you flip to the back of the assessment or test 1 or test 2 or your final exam, flip to the appendix, find the material properties inside the table. So here the property was not given, but the table is provided. So here you have a brass or rod, so cylindrical brass. So brass, you see, you have elasticity modulus, you have shear modulus, you have Poisson ratio. So basically you are recycling the Hooke's law or the E equal to 2G plus 1 plus Poisson ratio. So you'll still get the same answer because all these are linked under elastic behavior. Okay, elastic behavior. So in your experiment later, when you test the subject, you collect data and you use the table that we cover in the class or lecture. You compare the value you get and the value you see in the lecture or in the textbook. Right. So what is Poisson ratio? Poisson ratio is lateral divided by longitudinal. So just now you can find, right, in your lateral strain. So Poisson ratio here is 0.34. Substitute 0 to 34 in left-hand side. You have strain in X or lateral. You have strain in longitudinal. You have these two values already, right? So you substitute. You don't have the longitudinal because it asks you to change. It do not give you the change of length. It do not give you the change of length in a question. So there is one parameter missing, which is your longitudinal strain is missing here. So you move your missing parameter to the left. You press the calculator, you'll get 7.35 10 power negative 4 for longitudinal strain. Back to the definition of longitudinal is total change of length divided by original length, right? And then you relate to the Hooke's law, stress equal to capital E strain. Here you need to find the load. So you recall back what are the equations that you can use to find the load, which is stress equal to capital E strain. Stress is force divided by area. Okay, so there will be one of it that you can use. So here the force is missing. So you substitute stress equal to F divided by A equal to modulus Young and strain. Because modulus Young in the table you can find just now, right? Just now the brass modulus Young is 97 gigapascal. This value you substitute here. The lateral strain you can find. You find just now, which is lateral in this one. Sorry, not lateral. This one is longitudinal. Right, longitudinal. All right, so we substitute there. So stress in the longitudinal or uniaxial direction, in Z direction, equal to 97 gigapascal. Giga is 10 power 9. The strain you calculate just now, 7.3 something, 10 power negative 4. You press calculator, you find the stress. You get the stress, go back to the definition of stress, force divided by area. And you might ask, what are the area that should I use? Because they are change of area already, right? Which one? You use the original one, not the end result. You use the original one, then only you pull. So the area that you're using actually is before the pulling, before the action or before the loading. So the cross-section area that you use is the original section area. Okay. So area here, you know that it is a circle. Area of circle is pi r square or pi d power 4, pi d square divided by 4. Right? Then you move the equation, stress equal to force divided area. You move the area to the left, you get your force. Okay. So your stress is 71 megapascal. Mega is 10 power 6. Pi r square. So I divide the diameter. Here is diameter. So don't confuse with diameter and radius. Some of you are when you use pi r square, you straight away you take diameter. So it's wrong. Okay. If you use pi r square, remember to divide diameter into 2. If you straight away use diameter, you need to use pi d square divided by 4. Right? Because you square the r. Force will be 5,000 something. Right? So if you look at example 6, still testing your understanding in the elastic region equation. Are you able to call out what is stress definition? What is strain definition? What is the Hooke's law? How do you link? What is the Poisson ratio definition? And then what link the Poisson ratio and the elastic modulus, they all together, right? Or shear elastic together. Okay, so the one that I write on the whiteboard here, they are 3 marks in your solution. If it's needed, each one of it will cost you 1 point or 1 mark. 3 marks here. 25 points, you already get 5 marks if you write this one, this one, this one, this one, this one. Even though you don't know how to answer the question. You write this 5, you get 5 marks in your solution. Okay. So next one is like how we tell the story of metal behavior under loading. We use graph to represent the behavior. Right? So one of the tests is called tensile test. Right? And sadly to say, we don't have this machine. Right? But we have a simple one. We have a simple one. But I'll show you what is the standard machine. So because when you go to industry, when you start working, you will be seeing machine like this. Right? So don't say I don't know what is this. So you're studying mechanical, you should know what at the first sight you should identify what is this machine can do for you. So this one you have a machine. This machine is called tensile machine or tensile test machine. So tensile means what? You pulling. You pull means there's a 2 arm there that can pull the machine, pull the sample or specimen. So when you pull, then there is a sensor to sense the elongation. It still go back to this definition. When you pull, then it can calculate the strain. When you pull, there's a sensor for load. It can sense the force. And in the program, in the computer here, you can program what is the original cross-section area. So this one you collect by can up to 0.01 second, or it can even higher, right? Because we are now in the very advanced era. Our computing power is very good. So you can get very, very sensitive data. Then this small thing here is a cramp. It's a cramp. And before this, we introduce you one term. In one of the exercise, we introduce you a term called gauge length. either in example number 1 or number 2, I forget already. It's called gauge length. This is the original length that you measure. Where you use this original length? Strain. Okay, to calculate strain, you take change of length divided by original length. So this one, you cram the sample, you cram it, the computer will register the length. Then as you pull, the arm will extend. Since this is the sample, you will cram like that. So then you pull, this arm will, the leg will break, will extend. So when the break extend, it will register the elongation. Right? Elongation, then when it break, the program will stop the machine from pulling. Okay? Yeah. So this is called tensile machine. You study mechanical, you should, at the first sight, you should able to identify, oh, this is tensile machine. Right? So yeah, this is more diagram for you. So there are a few types of sample. First one, this is called rod sample because it's rod, and then there is a middle section here. So this is called gauge length. It is the original length that you use for calculation. This is called gauge length, and this is a rod sample. You have another sample. You have another sample called dog bone. You know how dog bone can also call dog bone, right? Dog bone means at the two end there you have a very big end section there. Okay, this is a rod. You can have a thin plate, referring to standard that you use. So just now, this one is the rod cylindrical sample. There's another one is called this one, the thin plate one. That sample, same. What is important is the gauge length. The size of the sample already defined in the handbook. When you want to test sample, want to test what, there is a standard that you need to follow. So you need to fabricate your standard according to the size, standard already, right? You test different material have different size, right? With a different thickness or different type of material, you use rubber material, also different size. Okay, let's see a video. Even though we don't have this machine, but it's good to expose you to this machine. It's called tensile machine and how it works. This is a sample. They have different type of grip. We call it grip. Different type of sample have different grip. If a rod, the grip was changed, the form is changed, but still you're able to hold the sample. So you can see the grip is different. This is a grip, the hand grip sample. So these are type of a sample. Okay. Okay. We are trying to get one for you guys, depending on the approval from the management. Okay. So once you see this one, I give you a sample of results that you can extract from the machine. On the left-hand side, always is a stress axis, sigma, and the x-axis is the strain. Okay. Now, how to plot this graph? How to plot this graph in experiment? Again, what is stress definition? Force divided by area. What is strain? Change of length divided by total length. Area, you can calculate before the experiment. You measure the diameter. You can calculate for area. If it's a round sample, then it's pi d square divided by 4 or pi r square. Length, you can measure. Total length, you can measure. So in your worksheet or in your lab worksheet, what you write? You write number 1, number 2, number 3, and so on. Then you write measurement 1. Measurement 1. You measure until it fails, right? Until it fails. So for force 1, maybe 100 Newton. Okay, this is the force and elongation delta L. This is L1. Means you measure the original length, LO. Then you apply 100 Newton. You measure the length. You get first L1, you have the force. Then second force, you apply maybe 200, 300. Then you measure the length again. Until the sample break. Until sample break, let's say maybe 1000 Newton, it break. Once it break, once the sample break, you join the sample back, you measure. That is the final length that you have. Okay, so this is the final length before it break. So how do you plot the first dot? You convert this diagram into number 1, number 2, number 3. You convert the first one into stress and strain. How you calculate stress? F divided by area. You have the force, right? Force convert to stress. You have the length, right? You calculate the change of length from the original length. You can get the delta L. So this one, maybe you change the delta L here. You get the delta L. Delta L, you calculate the stress or strain. Then point 1, you plot inside the graph. Go and find intersection point. Let's say 10 let's say 10 kilonewton, you get how many strain? Get first point, second point, third point until it fails. You only can get until here. Okay. Then the other one, this one is plastic one. You need a very careful measurement. Sorry, break is this point. Break is this point, but if you deal with a metal, then it break very fast. So break very fast is very hard to find all these points unless you have a very precision machine like the one that I showed you just now. Right? So when you get straight line, this straight line, you can get y equal to mx plus c. What is your y? Y is your E or Young modulus. Then the x is your strain. Recall Hooke's law. What is Hooke's law? Stress equal to modulus Young and strain. You get your modulus Young from the graph. Once you plot the graph, stress versus strain, you have all the dot. Maybe it is go haywire snake like that. But you know the Excel have a very powerful function. You can plot and then call the straight line, right? You know there's a function called straight line. Select this all this point, right click, add straight line. You will call a straight line like this. It will give you one function, y equal to mx plus c. It will give you something like y equal to 0.02 x plus something 0.01. This one is your E. From this experiment, you find the E for the material, then you compare back to all the textbook that you have. If you're given aluminum rod, refer to aluminum, then discuss why the value is different. Okay. The rest you read, huh? So, I already explained about the modulus of elasticity just now. Are you able to get the elastic of elasticity from the experiment data? Anyone still don't know? You know, huh? Okay. Let's say you get a perfect graph. Okay, let's say you get a graph like this. I draw something on the whiteboard here. You connect the line, you get a. Okay. You select all these, or you use the Excel function. You plot until here, then you find y equal to mx plus c. You find the modulus Young from here. The next one, from the graph itself, we will find the yield strength. Yield strength is what mean by yield strength? Yield strength is how many percent that you can use for your design. Like, for example, it's very hard to predict where is the plastic deformation start to happen. It's very hard. But theoretically and through many times of experiment, we already agree that we can achieve or we can identify plastic region by a certain calculation. We offset 2%, 0.2% from your strain. What I mean by 0.02%? It means, let's say you get 1 on the axis here. You take this 1, multiply by 0.2%. 0.2% means divide by 100, 0.2 divided by 100. So you get what? 0.002, right? If you get 1. Go and find 0.02 here. You know that when you plot a straight line graph, you can shift the graph down, right? You can shift the graph down, but the same gradient by changing the C, y equal mx plus c. It means you have this equation, you minus, this value, you minus 2%, minus 2, not minus 2%. You can minus 2%, and then you start from here, start from the x-axis there. Then you plot a graph, 2%. This dot is 0.2% offset. Okay, this point intersect with this point is where we assume, or where we assume that the plastic behavior start to happen. It start to yield already. It start to yield means it start to have a plastic elongation. Okay, so this is where we find the yield strength. Yeah, remember? If in your assessment, I give you an experiment data, then you plot on the graph, and then are you able to find where is the yield strength? You calculate y equal to ms plus c. You use your ruler. You calculate how many percent here on the strain first. Then you mark the location. You move your ruler. You put your ruler, shift down until your ruler touch this point. And then you draw a straight line. That line is your yield strength 2% offset. Then you get this point. You extend to the left. There's a value there. That is your yield strength. That value is your yield strength. Huh? Then the third one is called ultimate tensile strength. UTS. Ultimate tensile strength on the graph that you see is the maximum value you have on the graph. Maximum that you have on the graph. You see, the one that on the right on the screen is a maximum point 87 or 600 megapascal. It's the maximum point you have. Okay. Or it's a point. This ultimate tensile strength in your design, mechanical design, is the point that we don't want the end user to go. Right? Like for example, the leaf cable, the leaf cable. So it gives you like 20% inside the leaf. 20%, it give you a maximum kilogram there. That one is under safety factor or so and so. But that one, where they get that value is from the ultimate tensile strength. For example, the cable able to withhold 600 megapascal. But to be safe, maybe they divide by 4, maybe divide by 2. Then it's a safety factor, like it's a safety factor. So maybe divide by 2, you get 300 megapascal. So then you convert to the layman term. 600 divided by adults, maybe 80. So you get so many adults inside the. That is how you get the number of packs inside the leaf. Okay. So ultimate tensile strength is a maximum point that you can have on the graph. Percentage elongation at fracture. This one, if you read the statement here, it's just that you find the elongation. So you find elongation how many times 100 at fracture. So it means you join the sample together, and then you find percentage reduction in the area of fracture. So you take the fracture sample, you measure the diameter. Okay, compared to the original one. Modulus of resistance. This one I will explain later. Toughness, we will also touch on this one. So modulus of resistance, later I explain. Toughness, I will explain later. So far, what is important is modulus elasticity, how you do offset to find the yield strength. Are you able to identify where is the ultimate tensile strength on the graph, on the tensile graph? Okay, on the tensile graph. So all these are add-on information already explained. So on the graph, the first line, straight line, it fall under Hooke's law. It give you stress equal to the E and strain. Okay. First region there. Okay. So to find the E or modulus Young, you take the Y divided by X. Your Y is stress, your X is strain. Okay. Strain don't have unit, so stress is Newton over meter square or Pascal. Okay. So E is the measurement of stiffness or rigidity. So what is rigidity? Is the resistance to elastic behavior. Okay. Yield strength. Yield strength is show significant plastic deformation. Okay. Again, it's very hard to find yield strength. How you find yield strength? By the 0.2%. Okay. Some standard or some testing standard, they recommend you to use 0.02 or 0.0 something. It depends on the standard that you use. For our module on the textbook material, we use 0.2%. Maybe when you work in the industry later, your company, let's say you work in the industry where produce raw material, steel bar or something, your company have your own definition of yield strength. Okay, because the value itself is your company who have a final say. Okay, so when you buy material, normally they won't expose how many percent they use, but they will just give you one number. Okay, so again, we will, for American, they use 0.02. I already explained how to get 0.02, as you can see from the left-hand side diagram. You find 0.02, 0.002, you find here, put your ruler here, draw a line. Okay, now on the Excel, how you plot this line? How you plot? Are you able to do? How? If you already have raw data and then you want to plot on the Excel file. How? You have the raw data. So you have the stress and strain from the experiment. You have all this value, right? Let's say A1, B1, A2, B2, A3, B3. How you do 0.2% offset data here? You copy. Here, these two row give you what is E, right? You can find what is E, right? Because here, these two give you Y equal to mx plus C. You get the E already. What you do, you can replot what is the new stress and strain. You fix your, you can plot your stress will be the same, right? Stress will be the same, but strain you can shift a little bit. This one, you find the value already, but this one you, let me see, you rework the equation by considering 0.02% to here, to here, here, to here. So you can see what is the same thing. Your stress will be the same, but what is moving? Your strain value is moving. Right? Your strain value is moving by 0.2%. So you take this value plus 0.02% or multiply by additional 0.02%. Okay, multiply by 1.0002 in your Excel. Then you get a new one. You use a graph. You set on the same graph. You set this line on the graph. Then you compare. There will be one point that is overlapping. There's one value. There's one value here. There's the 1 point value between the new and the 2% offset. There will be one value that is overlapping or almost near between the experiment and the calculation. Here, you look at the table here. There's one value that very, very near. Okay, so this is how you do it, huh? Okay, I did tell you how to do, huh? So after experiment, I expect you know how to do. Okay, so I show you on my slide how to do it, the step and so on. Any question on finding the 2% offset? 0.2%. Enough? Enough? All right. So here you have a more simplified version, means you plot the 0.2%, then you extend the same parallel line with the red color line. You use the ruler, draw a line. Then the intersection point is the U point. Right. The ultimate tensile strength, or in textbook, they use sigma U to represent ultimate, the word ultimate, right? Sigma U is the maximum value that you have on the graph. Okay. Normally, you will see this value in most of the material specification. This is where the material, the maximum force or maximum strength that it can handle. After this one, the material, we call it as a, what's the engineering word? It's not safe to use, no longer safe to use after this force. So I'm from the aerospace industry. So if, let's say the aircraft for landed forced landing, the force is too big, although the structure do not break, the whole landing gear you have to change because it's already past the ultimate tensile strength. Although you say still at external it still look like new, but something changed in the properties already. Because at this point it already elongate already. It already in the plastic already. It already like compared to the original, it already extended a certain mm already, but it's not safe to use. You pull a little bit more, it will break. By looking at the behavior of the sample, for example, this one, especially aluminum material, you pull, when you see this reduction of we call diameter, we call it cone, cone behavior. Means it become a cone, become a cone. This one normally happen to the ductile material. Ductile material. So this is called necking. This one necking normally happen near the UTS behavior. This one is very obvious in aluminum sample. Other sample might not see this sample, might not see this behavior, unless you pull it very, very, very slow. Then most of the metal you see this one under high-speed camera. Okay, if you pull very, very slow, then you can see this one. But under normal speed, only aluminum is very obvious. You will see this behavior. Okay. Whereas you read. So these are the simplified diagram for you to imagine. So on the left, bottom one, this one is elastic, means no matter what are the force you apply, you release, you still come back to original shape. Then after 2% offset here, we start to yield, start to have plastic behavior, then cannot go back to original length. Maximum point is the ultimate tensile strength here. Then after this is continue to stay at the length that you pull. Right. Now on the left hand side of ultimate value here, the object still can go back a little bit after this point, before this point. It still can go back a little bit. But after this point, it will continue with the origin. How far you stop, you will stop there. After this point, the length will stay at that last loading. Okay, how you differentiate the left hand side and right hand side? Left hand side, they still see a little bit of going back to the original length, but after on the right hand side, you won't see any much of different compared to the last length that you pull. Right? So these are the two type of graph that you get if you overlap the graph. You use different type of material. If you have a higher brittle material, means the fracture will just fracture on that point and then it breaks. If you have a ductile, means it's like aluminum, you're able to pull until it breaks. Then you get a curved line like that, very long curve. Brittle means like ceramic. You pull, then you break like glass. Right? So by observing the graph behavior, you should able to tell like, oh, this is brittle material or ductile material. Okay? Okay. Percentage of elongation, this one you read. Okay, so this one is from the machine. You can measure again. This is the machine. This is called extensometer. It's a grip that measure the elongation of the object. Okay, you always say clip there. Advanced one, they no longer use this one. Maybe they use laser just to mark that. Then okay. Percentage of elongation is just your strain divided by elongation, longitudinal strain by 100. Let's read. So this is another table. You should able to tell how to use that one. You have yield strength. Okay. You have tensile strength. Don't confuse between yield and tensile. Don't confuse between yield and tensile. Yield is under 2% offset. This is the straight line. Okay, so don't confuse left and right. And then ductility display. I'll show you one formula to calculate. So these are the three different type of material. The red line, blue line, and green line. By looking at the diagram, are you able to tell which one is brittle material, which one is the ductile material? Then which one is more ductile? Okay, A is a brittle material. Then blue line, green line, they are ductile, but green one will be more ductile than the blue line. Okay. The rest is quite straightforward. Reduction of area you should able to calculate. Initial minus final. Why initial? Because initial always bigger than the final one in the metal reduction of area. Okay. Yeah. Okay, we have a short break. After the break, we come into application of the equation that you seen on the screen.